2016 Canadian Open Mathematics Challenge, Part C. A sequence of three numbers, ABC, form an arithmetic sequence if the difference between successive terms in the sequence is the same. That is, b minus a is equal to c minus b. These sequence 2b8 form an arithmetic sequence. Determine b. 2b and 8 are arithmetic sequence. Now, an arithmetic sequence is of the form a plus d, a plus 2d, and so on, a plus 3d, etc. So they've already given me that a is 2 right here. And then I also know that a plus 2d is equal to 8. So since a is 2, I can solve for d pretty easily. 2d will be equal to 6, and then d is 3. So since d is 3, I can find my b now. b is equal to a plus d. Well, a is 2, d is 3, and therefore b is equal to 5. Given the sequence ABC, let d1 be the non-negative number to increase or decrease b by, so that the result is an arithmetic sequence, and let d2 be the positive number to increase or decrease c by, so that the result is an arithmetic sequence. For example, if the three-term sequence is 3, 10, 13, then we need to decrease 10 to 8 to make the difference 3, 8, 13. We decrease b by 2, so d1 is 2. If we change the third term, we need to increase 13 to 17 to make an arithmetic sequence 3, 10, 17. We increase 13 by 4, so d2 is 4. Suppose the original three-term sequence is 1, 13, 17. Determine d1 and d2. 1, 13, and 17. So we have to make this into an arithmetic sequence by modifying either this term or this term. Right? That's basically what the question is saying. Okay, so let's fiddle around with this and let's see what we get. I think from here to here that's 12, and from here to here that's 4. Now, if from here to here we can make that 12, then that would be an arithmetic sequence. To do that, we would have to make that a 25. To make it into 25, basically what you're doing is adding 8. So by definition, based on what the question is telling me, since we increased c by 8, that means d2 is equal to 8. Entirely based on the question and its information. Okay, now we also have to find d1. Okay, so let's try to find d1. Well, our original three terms are 1, 13, and 17, and based on the definition of arithmetic sequence are of the form a plus d, and a plus 2d. Now, these are not obviously in an arithmetic sequence, so I don't want to confuse it by putting them there. So let's just say we have an arithmetic sequence. Any arithmetic sequence has a fundamental property that if you take the first term and the third term and add them, so the first term plus the third term, it would equal 2 times the second term. And you can clearly see that both sides are 2a plus 2d. So that's what we need to do. So in this one, we'll do the same thing. We'll take the first term and add it to the third term. So that's 1 plus 17. And that's got to equal 2 times the second term. So that means 18 is 2b, so therefore b would have to be a 9. So this would have to be a 9. In order to do that, we would have to essentially subtract 4 from the 13. And by definition, that means d1 is 4. That's essentially what the question is asking. Define d1, d2 in part B. As in part B, for all three term sequences, prove that 2d1 is equal to d2. Well, let's see here. We have A, B, and C that we start off with, right? And if they are indeed an arithmetic sequence, they're of the form a plus d, a plus 2d. And as previously explained, if you take the first term and add it to the third term, it would equal 2 times the second term. Now, I'm not going to put this because that's obvious, but I'm going to put this, correct? But this, the way they had given it, was not an arithmetic sequence. We had to make it into an arithmetic sequence by doing two things. The first thing we had to do is take this b and add or subtract from it that d1, if you remember, entirely based on what they said in the question stem. And then we had to take this c and add or subtract from it d2, right? So this is what we have to work with. But we have to prove this. Okay, so somehow, some way. But the interesting thing about this question is that they're not done at the same time. You either do it to one or the other. So for example, what that means is you either modify just b1 by itself by adding or subtracting d1, or you just modify c by itself by adding or subtracting d2. That's the key there. So this is actually not how it happens. Okay, so these are the two equations. Let's see what I can do here. So if I subtract them, if I subtract the second equation from the first equation, I will just get left with plus or minus d2, and I'll be left with plus or minus 2d1. Yeah. And I guess since d1, they told me in the question that they are positive, non-negative, so that means they're greater than 0. I just take the positive one. So that means d2 is equal to 2d1. And that's it. Alice and Bob play a game, taking turns playing on a row of n seats. On a player's turn, he or she places a coin on any seat provided there is no coin on that seat or on an adjacent seat. Alice moves first. The player who does not have a valid move loses the game. Show that Alice has a winning strategy when n is 5. Okay. So let's see here. Let's say n is 5. So we have to come up with a strategy. So who's winning here? Alice is winning. Well, Alice goes first. And then I guess Bob is second. And then it just sort of alternates from there. Alice and Bob and so on. Okay, so let's see what we can do here. If Alice goes first, put the coin on seat 3. Then Bob goes second. He can now only put the coin, his coin, either here or here. And let's just say he puts it here. By symmetry, the other scenario will be exactly the same. I'll just do one of the two possibilities. Then Alice now has to go, and she will then put a coin on that slot, which is slot 5. And then now Bob is in a situation where he has no moves, because based on the question, you can't put a coin in a slot that has a coin on the adjacent seat. So Bob loses. So that's the strategy. And like I said, it's symmetrical. So if Bob had placed the coin in this step on seat 5, it would pretty much be the same kind of scenario, just Alice would put the coin on seat 1 on her next move. So since Bob on this part, on that turn, has no valid moves, he loses. So that takes care of A. Now they're saying, show that Alice has a winning strategy when n equals 6. Okay, so the same sort of story, but this time there's 6 coins, or 6 slots, I should say. Actually, not 6 coins, but 6 slots. All right, so let's see what happens. Let's see what we can do. Alice, if she starts off, let's say she puts a coin on position 3. Then Bob now can put the coin either here or here or here. So let's just say he puts it there. If he puts the coin here, then Alice now can put a coin either here or here. So let's say she puts it there. And now Bob, unfortunately, has no place to put a coin. So Bob loses. Okay, so that's part of it. And then the other way was, of course, sort of similar. She starts off there, and then Bob, let's say he decides to put a coin, let's say here. Then Alice would put a coin here. And then now that it's Bob's turn, he unfortunately has nowhere to go because this slot, and this slot are taken, and he loses again. So Bob loses again. So I think there's one other scenario, which is that Alice puts the coin here and then Bob puts the coin here. And I encourage you to do that one and see that, again, Bob would lose because Alice would then put the coin there and then Bob would have no slot because he can't put it here or here or here because those slots have adjacent coins. So, okay, so that takes care of that. Now let's get up to Bob has a winning strategy when n equals 8. Okay, n equals 8 this time. Okay, n equals 8, I'm going to need a lot of space, so I'll just pull it all up. So n equals 8. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. All right, so Alice, Bob, and so on, right? Alice, Bob. Let's just see how far we need to go. Okay, so Alice goes first, so she can put a coin. Let's say she starts putting the coin here. Now, because of the symmetry, the other choice, there was several choices here, but coin 1 and 8 will behave in the same way. So I'll just put 1 or 8 as the first choice. Then Bob can go. There's already a coin there, so he can only place a coin in those 6 slots. So he can put the coin anywhere in here, correct? So now this actually becomes a scenario of an n equals 6. And just like how we did before, it becomes essentially just this n equals 6 kind of scenario. And if you follow the same strategy, you can make Bob win. The reason is because, see, Alice always goes first, right? But once you get down to here, you see this becomes a completely different ball game. This is n equals 6, but now Bob is going first. So it becomes an n equals 6 scenario with Bob going first. And since that's the case, all he has to do is just use this strategy shown in part B, and he can win exactly here, because here the strategy was the same. The only difference was that Alice was going first, right? But in this one, it's n equals 6, but this time it's Bob's turn. Bob is making the first move. So n equals 6 scenario with Bob going first, use same strategy as in part B of this question, and that will make Bob win. Okay, so now let's do the same thing, but this time we have to select something different now. So the one, if Alice puts a coin in position 1 or 8, that's the scenario, this whole thing. Now, let's say she puts a coin in position 2 or 7. So either here or here. And by symmetry, position 2 or 7 will behave in the same way. If she does that, then Bob now has no choice but to put a coin in those 5 spots. So now it becomes an n equals 5 scenario for Bob with Bob going first. And therefore, you use the same strategy as in part A of this question, and that will allow Bob to win. So if you recall, we had this basically scenario, and you just do the same thing, but the only difference is instead of Alice going first, Bob goes first, and that allows Bob to win using that strategy. Okay, so we've taken care of the 1 and 8, the 2 and the 7. Now we still have to talk about the other spots, which are 3, 4, 5, 6. Okay, we can do that. So let's say we have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. All right, so let's say Alice puts the first coin in slot 3 this time. So she's there. Then what Bob does is he can put his next coin on slot 1, 2, 3, 6. So that's going to be here. And then we proceed, and the coins are already here. Then Alice, let's say she's got sort of a limited choice. She can only put the coin here or here. So let's say she puts the coin here. And then now Bob, 1, 2, 3, 4, 5, 6, 7. So the coins are here. Bob then places the coin here. And now that's Alice's turn. She has no valid move to make because all the slots are filled, and you can't put it here, here, or here, or here because those slots have adjacent coins. So that means Alice loses, Bob wins. And then by symmetry, if the first coin was on slot 6, it would be the exact same. So this takes care of 3 or 6 with regard to the first space that Alice puts her coin. And then one final scenario, which is where she puts the coin on slot 4, and by symmetry it will be the same as slot 5. So let's go through that whole big long song and dance. So Alice, Bob, Alice, Bob. So Alice, first coin on slot 4. That means then Bob can choose slot 6. And then we can have Alice. Well, at this point, she has very limited. She can only use either these two or this guy. So let's say she decides to put the coin here. Then Bob can easily win the game by putting the coin either here or here. And then that's it. Alice has no valid options, so Bob wins again. And I encourage you to kind of experiment with this, and you can see that no matter what scenario Alice chooses for this move, Bob can always sort of find a way to win. So that's all it is. It's really just a way of fiddling around and finding different strategies, and also save yourself some time by noticing that they're symmetrical. So if the first move is either 4 or 5, it kind of behaves exactly the same. If the first move by Alice is 3 or 6, it behaves the same. And then similarly for 1 or 8 or 2 or 7. Let A, 0A, 0, 0, C0, CB, where A, B, C are positive integers, P is P0, be the point on line segment OC that minimizes the distance AP plus PB over all choices of P, and X is AP plus PB. Show that the minimum distance X equals C squared plus A plus B squared under the radical sign. All right, so let's draw a diagram first. So let's draw a diagram here and explain this. So let's label this. This is, of course, the origin right here. And this is, of course, the x-axis and the y-axis. And then this point right here is your A, which is 0A. And then this point here is C, which is C0. And then B is up here somewhere, so this is B, which is CB. And then this point, I guess, is P, which is P0. Now, what they're saying is that they want you to figure out X, which is AP plus PB. A to P plus P to B. And in particular, they want you to figure out the minimum value of that. Well, what you do is you extend the line AP down to that. And really what that is you've reflected this B in the x-axis. So this distance is the same as that distance, like a mirror reflection. So this is my new B prime, and the coordinates would be C, negative B. So if you were to go across to the y-axis, it would basically be minus B down here. Okay, so let me just draw a dashed line there like that, just to kind of show you. Okay, so now the minimum distance x is really this straight line, because this distance PB is the same as this distance B prime. So minimum x is your AP plus PB prime. And then that really is just A to B prime. And A to B prime you can get using Pythagoras. So AB prime squared would be this part squared, which is what, C squared, right? Yeah. Plus this part squared, which looks like A plus B, right? Because the distance from here to A and the distance from there to there is B, because you have to use the positive value. And therefore AB prime would be the square root of C squared plus A plus B squared. And that's exactly what this is. C squared plus A plus B squared under the square root sign, and that's what they wanted you to show. If C is equal to 12, find all pairs AB for which A, B, P, and X are positive integers. All right. So we will give A plus B a value, and I'll call it n. And we know that x squared is equal to C squared plus A plus B squared under the square root sign, right? That's what we had in our previous part right there. So with the substitution, it will be a C squared plus n squared under the square root sign. Square both sides, and you get x squared is equal to C squared plus n squared. And then C, they told me, is 12, so I can make that substitution. X squared, therefore, is 144 plus n squared, like that. And therefore, 144 is equal to x squared minus n squared. And then that factors nicely to x minus n, x plus n. There we go. Okay, so now we can make a little table, x minus n, x plus n, and then x and n, and see what kind of values we get. So what kind of values? Let's see here. We can have 2 and 72, 4 and 36, 8 and 18, 12 and 12, and 24 and 6. And you can solve for x and n. For example, I'll just do the first one. If x minus n is 2 and x plus n is, say, 72, you add both equations. That will give you 2x is 74 and x is therefore 37. Sub it back into here and you'll get n is equal to 35. So in a very similar way, you can figure out all the other ones. And they are 20, 16, 13, 5, 12, 0, 15, and 9. Okay. Now, this solution is no good because n can't be 0, right? Because n represents a plus b. And a and b are positive distances. So we have to then just sort of experiment with these values and see what we get. So let's do that. So for those 4 values, let's see what we get for a and b. So if you remember in our original equation, our original diagram, we had a scenario where you kind of had this, right? And this was P right here, from here to here. So that was P. This distance was P. So since that distance is P, and C they've given us as 12, which is the distance from there to there, you can use a similar triangles that P over 12 is the same as from there to there over the full distance. So from there to there would be A, and the full distance is A plus B. So that's just using similar triangles. So we'll use that as our guideline, that P over 12 is equal to A over A plus B. Now A plus B we had called N up here, if you remember right up there. So that's just N. So P over 12 is A over N. So therefore P is equal to 12 times A over N. And then let's figure it out for N equals 9, N equals 16, and then 5 and 36. So I'll do the first two, and then the other two, they actually have no solutions. So I'll let you guys do that, but I'll do the ones that have solutions, 9 and 16. Okay, so if N is 9, what do we have? If N equals 9, then that means that P is equal to 12 over 9 times A. Now we want A and B to be integers. So the way you can get A to be an integer is if A is 3, or if A is equal to 6. And if that's the case, then P values would be 4, the B value would be 6. And the way you get B, of course, is that A plus B is equal to N, and that's how you got B, because N is 9. And if A is 6, then my P value ends up to be 8, and B equals 3. So there you go, we got two pairs, namely 3, 6, and 6, 3. So that's for N equals 9. And then I'll do the last one, which is N equals 16. If N equals 16, then that means using that formula, we have P is equal to 12 over 16A. And then the values of A that would be integers, A equals 4, A equals 8, and A equals 12. The corresponding values of P would be 4, 6, and 9. And then the corresponding values of B would be 12, 8, and 4. So there we go. We got a few more doubles or pairs, and that is 4, 12, 8, 8, and 12, 4. So there we go. Those are the triples, or the doubles, or pairs, whatever you want to call them, that they're asking for. If A, B, P, X are all positive integers, prove that there exists an integer n greater than or equal to 3 that divides both A and B. Alright, so I'm going to first start off by making a little bit of a substitution, that the C minus P, I will call it K. And therefore, C minus K will be equal to P. And then just as before, by similar triangles, if you remember, we had made that relationship that P over C was equal to A over A plus B. Remember? Right up here. Right up here. Well, C was 12 in that case. That's why we put a 12 there. But it was really P over C is equal to A over A plus B by similar triangles using that diagram. So we use the same thing, but this time we just have C as C. So when you cross multiply, you get P is equal to AC over A plus B. And now this P, I have called it C minus K, so I'll call it C minus K is AC over A plus B. And then let's isolate just for k. So k would be c minus ac over a plus b. And then I have to add these fractions, so get a common denominator. So that's going to be ac plus bc minus ac over a plus b is equal to k, and the ac's cancel. So all we're left with is bc over a plus b is equal to k. Okay, so now we have to look at this guy and talk about a few things. Let's say I have some variable n, and it is the smallest integer such that n times c is divisible by a plus b. Now, if that's the case, and we already know that p and this k up here that I introduced are integers, then that means that n must divide both a and b. So both a and b. All right, so now we experiment with values of n. Let's say we set n equal to 1. Then we see if nc over a plus b is divisible. If it is, it would equal some integer. So let's call it I1, where I is some integer element of the integers. Cross multiply and you get c is equal to, well, n is 1, so that's just going to be I1 times a plus b. Correct? Now, we recall our relationship that x is equal to c squared plus a plus b squared under the square root sign. You remember that? So that means x is going to be, we substitute this in, I1 a plus b all squared plus a plus b squared under the square root sign like that. And this would therefore be, let's see here what we get. We would get a plus b squared, I squared, and then I can, I1 squared that is, and then plus 1. And then this will be all under the square root sign, and then I can kick it out. It would just be a plus b, and then it would be I1 squared plus 1. Okay, so they're saying that this is an integer. This is an integer when the only time this will be an integer, x, is if this is an integer, and that happens when I1 is equal to 0. So x is an integer when I1 is equal to 0. But if that's the case, then if you look up here, that would make c equal to 0. And of course that's not allowed because c has to be a positive integer. So when n equals 1, this all falls apart. Okay, not a problem. Let's just keep going here. Let's try n equals 2. Let's see what happens. When n equals 2, in a very similar way, we've got nc over a plus b is equal to, let's this time call it I2, where I2 is an element of the integers. So that means 2c, because n is 2, is equal to I2 times a plus b. And again, we do the same thing that we did over here. We substitute it into this formula. And when you do, you get x is equal to I2 a plus b over 2 all squared plus a plus b all squared under the square root sign. So that then if you multiply this all out and factor, you'll get I2 squared over 4 plus 1 under the square root sign. So that means this will be a plus b, and this will be I2 squared plus 4 under the square root sign, and then the 4 can come out as a 2 like this. Okay, now let's look at this. X is an integer this time when I2 is equal to 0. But again, that makes C equal to 0, since it would, if you plug I2 into that equation. Then of course that is not allowed again, since C has to be a positive integer. So n equals 1 does not work, n equals 2 does not work, and you will find n equals 3 will work, and so on. N equals 4 will work, and I'll let you guys do that. So basically what it means is that for all values n equals greater than or equal to 3, this will work. And that's essentially what they wanted you to show. That when n is greater than or equal to 3, this whole scenario will be valid. That n is the smallest integer such that nc is divisible by a plus b, and since p and k are integers, n must divide both a and b. Two lines intersect at a point Q at an angle theta, where theta is between 0 and 180. A frog is originally at a point other than Q on the angle bisector of this angle. The frog alternately jumps over these two lines, where a jump over a line results in the frog landing at a point which is the reflection across the line of the frog's jumping point. The frog stops when it lands on one of the two lines. Suppose theta is 90, show that the frog never stops. Okay, so we have a scenario where, let's just draw a basic diagram. We'll call this L1 and we'll call this L2. Okay, and then the frog is initially on the angle bisector. So this is 90 degrees, so the angle bisector obviously cuts it where that's 45 degrees, and this is 45 degrees, correct? All right, so I'll put the frog right here, F for frog. Now, entirely based on the definition of the question, the frog then jumps over the line and jumps over a line to a point which is a reflection across the line. So what that essentially means is that if we were to draw these reflections, then the frog essentially jumps in a way so that that L1 becomes a mirror. So it'll go right across to here. Okay? Entirely based on what the question tells you. And then the frog is here. And then it behaves in a way that it uses that line as a reflection, and it jumps over that line at a point which is a reflection across that line. So then it would end up somewhere here. And then similarly, it would use that line as a reflection and jump to here. And then in a very similar way, it uses that line as a reflection and jumps back to here. And that just keeps going. It keeps going round and round and round, and therefore it actually never lands on one of these original two lines, because it has to land on one of those two lines in order to stop. And because it never lands on one of those two lines, it never stops. And that's essentially all that part A wants you to show. Part B, suppose that the angle this time is 72 degrees. Show that the frog does eventually stop. All right, so now we got a little bit different. So now we have a slightly different scenario. This time we have 72 degrees. So let's just say this is L1 now, and this is L2. So this is 72. And that angle bisector breaks it up into 36 degrees and 36 degrees. So the frog, let's just say, is here. Okay, so based on the definition, we now have to use this as a reflection and go across that line in a way so that the frog ends up on the other side of the line, landing on the reflection point. So the reflection point also has to be 36 degrees from this side. So I'll just draw it approximately like this, right? So that this is now 36, and now the frog apparently approximately there. So it's not perfectly drawn to scale, but I hope you understand. So now again, the frog has to use that line as a reflection and go on the other side exactly the same way. Now we have to figure out this angle. Well, all of the angles would be 180, so you have to take 180 and subtract from it these 36s. So minus 36, minus 36, minus 36. And when you do, you get 180 minus 108, which is 72. So that means this angle in here is 72. So we've got to go 72 degrees in that direction in order to end up somewhere here, right? The reflection would be approximately here. Well, guess what? If the reflection lands exactly on L1, which it does, the frog then eventually stops, because the frog stops when it lands on one of those two lines, L1 or L2. So there you go. That shows what they wanted us to show in part B.